Hi everyone. Today we'll solve a related rates problem involving a balloon. A spherical balloon is being filled with air at a constant rate of 5 centimeters cubed per second. To visualize this, let's draw a picture. Here is our balloon. Our balloon is a sphere. Because it is a sphere, it has a radius. Let's add it to the picture. We are also told that this balloon is being filled with air at a constant rate of 5 centimeters cubed per second. To denote that, I will add an arrow pointing toward the balloon, and right next to it, I will write 5 centimeters cubed per second. We must determine how fast is the radius increasing when the radius is 10 centimeters. We need to know the rate of change of the radius. In other words, we need to know the derivative of the radius. So we are looking for dr dt. And we are looking for dr dt when the radius is 10 centimeters. We were told that the balloon is being filled with air at the constant rate of 5 centimeters cubed per second. So now ask yourself, what is changing at the rate of 5 centimeters cubed per second? I believe it is the volume of the sphere. So you can say that the derivative of the volume of the sphere with respect to time is 5 centimeters cubed per second. For now, I will suppress the units and I will just write it as 5. We are given one rate and we are supposed to find another one. What's more, those rates are related. The faster the air comes into the balloon, the faster the radius will be growing. And the slower the air comes into the balloon, the slower the radius will be growing. Can we find some equation that relates the volume of the sphere and the radius of the sphere? There is an equation like that. It is an equation for the volume of the sphere. It is that the volume of the sphere equals 4/3 pi r cubed. This equation relates v and r. However, I need an equation that will relate dv dt with dr dt. So I need to introduce derivatives to this equation. The easiest way to do it is to use implicit differentiation. Take the derivative on both sides of this equation with respect to time. If you are not sure what implicit differentiation is, I will add a link in the video description leading you to a video in which I talk about implicit differentiation in detail. So now I take the derivative on both sides with respect to time. If I take the derivative of v with respect to time, I will get dv dt. On the right side, I have 4/3 pi is a number, r is a function. So when I take the derivative, I use the constant multiple rule. I rewrite the number and then take the derivative of the function. So I rewrite 4/3 pi, and then I take the derivative of r to the third power. Remember, r is a function of t, which means I must apply the chain rule. There is the inside function r and the outside function third power. So when I take the derivative of r, I get dr dt. When I take the derivative of the third power, I get 3 inside function squared. Let's simplify this equation and solve it for dr dt. The first thing I see is that I have 3 in the denominator and 3 in the numerator, so I can divide those out. Then I get that dv dt is 4 pi r squared dr dt. My goal is to solve for dr dt, so I will divide both sides by 4 pi r squared, so that I have dr dt by itself. That gives me dr dt is equal to dv dt divided by 4 pi r squared. Remember, you want to find the derivative of r with respect to t whenever the radius is 10 centimeters. So what you're looking for is the derivative of r with respect to t whenever the radius is 10 centimeters. So you know that in your equation now, you can replace r with 10, which will give you r squared, which is 100. What's more, you know that the rate of v with respect to t is always 5 centimeters cubed per second. Note that it was a constant rate, so it's always 5 centimeters cubed per second. So you can replace this rate with 5 and this r with 10 and solve for dr dt. If we do that, we get 5 over 4 times pi times 100. I plugged in 10, 10 squared is 100. So that gives me 5 over 400 pi. And the units were, the units of the radius were centimeters, the units of time were seconds, so this must be centimeters per second.